Welcome back, geometry students. We are in Chapter 8, first section, Similarity in Right Triangles. Please pause the video, try these problems, and come back to check your work. Okay, welcome back. Writing the similarity statement gives us this. Triangle ADB is similar to triangle EDC. Now, of course, you could have written it differently, but make sure that A corresponds with E, D with D, and B with C. Square root of 72 equals 6 times the square root of 2. Square root of 27, 3 times the square root of 3. Solving this, we have x equals 24 over 5, or you could say 4.8 or 4 and 4/5. X equals plus or minus 5, right? So when you take a square root, you have the option of a principal root or the negative root. Today's objectives are to use a geometric mean to find the segment length in right triangles. Also, to apply similarity relationships in right triangles to solve problems. So, geometric mean is the term that you need to make sure you fully understand by the end of the lesson. In a right triangle, an altitude, imagine, we think often of the word height, right? An altitude drawn from the vertex of the right angle to the hypotenuse forms two right triangles. The next slide shows you this image, right? We have a right triangle, ABC, and the altitude formed from the right angle C to the opposite side, right, forms a 90-degree angle with that opposite side. When we have this scenario, we find that the two triangles that are formed when we by this altitude, the little triangle here, BCD, and this medium-sized triangle, CDA, right? They are similar to each other, and they are similar to the original triangle ABC. Okay, so if we look at ABC, the large triangle, and we look at ACD, we see that in ABC, the right angle is C, right? In ACD, the right angle is D, right? And then in CBD, the right angle is D, okay? And then we look for the other corresponding angles. Make sure you're very careful when forming a similarity statement. So write a similarity statement comparing the three triangles formed in this image here. Now there is more than one way to write this similarity statement. As we compare your answer to the answer given, let's just make sure that you have the same corresponding angles. Okay, so pause the video, come back and check your work. As was seen, you could sketch each of the right triangles out separately. Often that is a great strategy for seeing things clearly in geometry. So we have the large triangle, UVW. You can see that the right angle has been brought down. The whole thing has been tilted a little bit, rotated toward the left. U has dropped down a little bit, and we see this beautiful right angle, W. Looking at the medium-sized triangle, where is the right angle? Up here, Z. So that has been rotated around and even reflected so that we can see the orientation of the angles. And the small triangle's right angle is Z. So here we have one way we could make this statement. UVW is similar to UWZ is similar to WVZ. Okay, as long as your angles correspond in this same way, you have a correct answer. Okay, if we consider this proportion, we notice we have a common term in each ratio, right? In this case, the means, now in a proportion, we have what are known as means and extremes. The means, when we say the proportion, it's A over X equals X over B. The means are the two value expressions that we said in the middle there. A over X, X over B. The extremes are the first and last thing that are stated in this proportion. A and B are extremes. The means are, in this case, both the same number. So the number is the geometric mean of the extremes. So what does that mean? The geometric mean of two positive numbers is the positive square root of their product. So if we were to simplify this, I could multiply both sides by x, bringing x up here, right? And multiply both sides by b, which brings b up here. So cross products, right? Bring the x up, bring the b up. And x times x up here gives us x squared, right? And x squared equals ab. You can see that. So the geometric mean of a and b is the positive number x. So that if x squared equals ab, then when we take the square root of x squared and the square root of ab, x equals the square root of ab, as you see here. Okay? Because x equals the square root of ab, if I square both sides again, we're back to x squared equals ab. So the geometric mean of two positive numbers is the positive square root of their product. So let's try to apply finding the geometric means. So this can make more sense using real numbers. So find the geometric mean of each pair of numbers. If necessary, give the answer in simplest radical form. I have the numbers 4 and 25. We're asked to find the geometric mean. So let x be the geometric mean. So x squared equals 4 times 25. So we multiply them together and we have x squared. That's by our definition of geometric mean. So if we want to find the value of x, we simply take the square root of the left side, take the square root of the right side, and the square root of 100 is 10. So we have the positive root, okay? We're finding the positive root because it's typically a dimension that we're finding. So go ahead and find the geometric mean of 5 and 30 and come back and check your work. Okay, so x squared in this case equals 150. When we take the square root of 150, we have 25 times 6 inside, right? So it equals 5 times the square root of 6. Because an altitude of a right triangle forms 3 similar triangles, we can set up a proportion that involves all of these triangles, right? So if I look at the original triangle here, we have length b over a. So here we have the longer leg over the shorter leg of triangle ABC, right? So the longer leg of triangle ADC is y over the shorter leg is h, right? And then if we look at the small triangle, the longer leg is h over the shorter leg, which is x. So we can set up this true ratio, right? This true set of proportions, and notice we have a geometric mean in the red proportion here. We have the denominator and the numerator of the denominator of this ratio equal to the numerator of this ratio, so there is a geometric mean, okay? So we can also say that C, which is the hypotenuse of the large triangle, is to A, which is the shortest leg, as B in the middle-sized triangle is to H, shortest leg, as A, which is the hypotenuse of the small triangle, is to which side is the shortest in that triangle? X, that leg, right? So notice that the first ratio and the last ratio have geometric means. They both have A, one in the denominator, one in the numerator. And finally, we can make another set of ratios where C is to B, which means the hypotenuse to the longer leg, as B is to, here's a longer leg, right, Y, and as A is to H. So again, we have a geometric mean. This leads us to the geometric means corollary. The geometric means corollary says the length of the altitude, h, to the hypotenuse, of a right triangle is the geometric mean of the lengths of the two segments of the hypotenuse, x, y. We just found that in the previous slide's proportions. So h squared equals x times y. And the length of a leg of a right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So a squared equals x. This is the segment of the hypotenuse that's adjacent to a, right? X times the hypotenuse, c. Or b squared equals y, which is adjacent to b, times c. Okay, so given what we've just learned, can you find x, y, and z? So 6 is the altitude, so the first corollary tells us that 6 squared equals 9 times what? Hopefully you said x, right? 6 is the geometric mean of the 9 and 6, right? So now we simply can say that 6 squared is 36, divided by 9 is 4, right? So we have an x value of 4, so fill it in, right? Okay, y squared equals, do you remember the relationship in the second corollary? Something times something, right? It equals 4, which is what we just found, the piece of the hypotenuse adjacent to y, right? 4 times 13, the entire hypotenuse. 4 times 13 is 52. So we're going to have to take the square root of both sides, and y equals the square root of 52, which is 52 equals 4 times 13, so 2 times the square root of 13. And finally, z squared. Can you finish it? Come back. Good. 9 times x, right? 9 times the hypotenuse, which is 9 plus x, so 13. And so z equals 3 square root of 13. Here's a great helpful hint. Once you've found the unknown side lengths, you can use your Pythagorean theorem to check your answers, right? If you have time, it's a great check. So here we have an application of the use of the geometric mean corollaries, right? So to estimate the height of this Douglas fir, Jan positions herself so that her lines of sight to the top and bottom of the tree form a 90-degree angle. Her eyes are about 1.6 meters, you can see here, from the ground, and she is standing 7.8 meters from the tree. So we're trying to find the height of the tree to the nearest meter. Okay, so we're using which corollary? Good, the first one, right? Where we have the altitude squared equals 1.6 times x, right? So we can solve for x by squaring 7.8 and dividing by 1.6, which is approximately 38. So 38 plus the 1.6, her height, equals 39.6, or about 40 meters tall. So geometric mean is a great way to find the height if you have these other measurements. You might see surveyors doing that on the roadways around town. Speaking of surveyors, surveyors do things like mapping, and they help us with topography, so the heights of things and so on. So pause this and see if you can find the height of the cliff to the nearest foot. Come back and check your work. We're using the same corollary, aren't we? So 28 squared equals 5.5 times the unknown x, right? And so we find that x equals 142.5. Now to find the height of the whole cliff from the base, we'll add the 5.5, and we have 140 feet high. Good. So please pause the video and try the lesson quiz. Come back and check your work. The geometric mean of 8 and 18 is 12. The geometric mean of 6 and 15 is 3 square root of 10. Again, pause the video, come back and check your work. Number 3, one way you might have written the statements. Number 4, 5, and 6. Good. Here is your assignment. You might have to go back and pause that if you want to look at those. I'm done.